And now the key person is our speaker today. This is Mihail Petrov, who is working as assistant professor in ITMO University. And the topic is more like a close to mechanical engineers, because it's about acoustics, something about metamaterials. Please welcome Mihail. He's enjoying already second day in Tashkent, and we see how he likes us.
Thank you very much. Is it okay that I'm not using the speakers, or is it okay, right? I'll try to be maybe louder because I'm not sure it will improve. Thank you very much, Mihail, for a nice introduction and for welcoming me here. I'm really enjoying this only second day, but I like the scenery, I like the place, and I hope truly that there will be some future connection, and that's my first, but definitely not the last visit to New Uzbekistan University and Tashkent. So our talk today will be related to acoustic metastructures and acoustomechanics. And just to show you the outline, so I'll start with some introduction. I will introduce myself in a few slides and our lab, and then first I will go consider a simple Fabry-Perot type acoustic resonator, and then we will switch to some problem of scattering of acoustic waves on metastructures, and what can metastructures give us, and then some acoustic forces, and finally I will show a few slides on our projects on meta lenses. So it's a bunch of different topics. I tried to put them all together. Definitely not all our directions are covered, but still, for the sake of some integrity, I chose this one. So I'm leading quantum nanophotonics and optomechanics group. So it's a young group, predominantly of PhD and undergrad students and a couple of postdocs. And we do nonlinear nanophotonics, optical forces, quantum nanophotonics, and acoustics since recently. And acoustics is one of the main experimental directions because we are more theoretically oriented people. And our acoustic lab is actually just a couple of years since we started doing acoustics. So this is our lab on the left, and these are the students working there. A few setups. These are tabletops setups and quite easy to build, so nothing too fancy. Here is on the right, so I don't know, the laser pointer doesn't work, so I'll be somehow waving my hand. So here you see on the top, this is one of the setups. So it's just small anechoic chamber, just a box. We also have a huge anechoic chamber, which is used normally for microwave physics. It's tuned for that, it's built for that. But we use it for acoustics as well, because if you will get inside, you immediately hear that you cannot hear any noises at all. So it really absorbs sound also quite well, and we use it. So last year, I just wanted to show that our activities are already getting at the international level, and we had an international school on acoustics last year. It was conducted in China, in Qingdao, with our partner university, Harbin Engineering University. So maybe just next time it might be in Tashkent, I don't know, or whatever. But just to switch to some scientific part, let me start with just few basic slides regarding the acoustics, so we could be at the same table. So what I'll be considering mostly, these are acoustic waves, which are longitudinal waves, dense waves of density in, let's say we are thinking of air, so it's homogeneous isotropic acoustic, so it's not a solid state acoustic, for example. It will not be covered at this time. So what you have pressure and density. So normally you have some default pressure. So atmospheric pressure and some density. And then what we are considering is the some kind of a, I'm sorry, it doesn't cover. So should I? I'm afraid to do that. So, but normally we are considering some addition of, so what is acoustic wave? It's some addition, tiny deviation from atmospheric pressure, right? So we are considering only this part, and V is the velocity of acoustic of atoms, right? Of these waves. Normally, so you would consider this pressure in a perturbation theory. So all what we are hearing now, it's a just tiny deviation, because normally you have huge atmospheric pressure and only some little changes which we hear. In ambient condition, there is no velocity, but acoustic wave generates some velocity. And if you go and make some kind of a decomposition of pressure in terms of density up to first order, here you will have what is called square of sound velocity. So, and all what we are interested in are these quantities at the bottom. So you want to know the pressure at each point in space and time. And why it's so the master equations are the following. So the first is a Newton equation, yeah, just which connects velocity, so acceleration and force. So gradient of pressure here, just the force, and this is the continuity equation. Yeah, just the mass conservation, and this is equation of state which connects pressure and density. This is, let's say, phenomenological law, right? The control parameters are compressibility and mass density. Yeah, so this is inverse derivative of pressure over volume, and mass density is quite clear. Both together, being combined, they provide you a velocity, sound velocity. So you need to know compressibility of media and density of media, and that gives you velocity of sound. So this system of equation, of course, are universal wave equations. And why we are I am personally, and people doing nanophotonics and optics are interested in all that, because there is So in a monochromatic field, this equation gets even more simple, and you just change the time derivative over the multiplication over frequency, and then you come up with the equations which are very similarly, in many senses, they correspond to Maxwell equations. Now, instead of epsilon and mu in media, you have compressibility and density, and instead of set of Maxwell equations which connect E and B, you have equation for pressure and equation for velocity. Of course, fundamentally, these are very different equations and symmetries, etc. But the wave physics might be very similar, and I'll try to show you how does it work. One of the examples of acoustics, I'll show a few slides just to motivate our interest in acoustics and why it can be so cool. These are just experiments with acoustic levitation. My last part of the talk will be more about there will be more details about this. This is a simple setup. You can make it even not in your lab, but just at home. It's quite easy to do. However, the physics is complicated. But just to try to give you some understanding of this field. So this is the acoustic tweezer. So single beam. So this is acoustic. This is basically a speaker. And there is a lens, and it focuses sound and holds one particle. So this is called single beam acoustic tweezer. So the funny thing that the paper where people invented it. It was published in 2016. By matter of fact, the same optical system, which does the same for microparticles, so it was invented in 1986 by Arthur Ashkin, who is Nobel laureate. So it took 30 years somehow to do the same what was done in optics, which is much more, let's say, complicated and sophisticated field. So to repeat it in acoustics somehow, so this is the, let's say, gets you some understanding of the development scientifically. So the approaches which were developed in 1986 were realized only 30 years later. And that's why we are doing this, because there are many, many blind spots where we can contribute with our nanophotonic and optical knowledge. And maybe this is also quite, this is not our work, this is work from nature yet. With many transducers now you can control a single particle, rotate it, or transfer or move it around the platform. So that gives you very like a precise control of single particle only by acoustic waves. So let me start with a simple acoustic. What could be the simplest thing? It's acoustic resonator or Fabry-Perot type. Just a cavity. So imagine you have a tube, loudspeaker at the one end, and then you can put a microphone inside. So this is a closed cavity, just a resonator. If you do that and measure, you can measure quite easily all the spectrum. So in this graph, what we see is the frequency and then the distance when you move the microphone along the cavity. So you have, let's say, 2 maximas, 3 maximas here, etc., etc. So more and more. So these are the standing waves, basically, at higher and higher frequency. You can measure the quality factor of this system. You see, for each mode, the quality factor varies, rising up to 400. So 400 is quite a lot for simplest. This is a plastic tube, and the quality factor depends on the losses, like on the losses in material. Now, if you couple two resonators, now you see this is T-shaped coupling. And another thing what you can do, you can change the position of this mirror, and the second mirror for the second resonator actually is water. So you control the level of water, and that's how you can easily control the length of the resonator. Why do we do that? Because that allows us to fastly scan the position without any mechanical setup. So you just change the water level, and that changes the frequency. And then when you tune one of the resonators, when you change the water level, you change the resonance of the bottom resonator too, and you see how and you measure the amplitude of the field inside, and when they cross, so this is the mode of resonator 1, and this is the resonant mode of resonator 2. Once they hit, they start to interact at the same frequency, resulting in this kind of a type, we call it anti-crossing regime. So here, what we did, we just controlled the size of the coupling here. So the larger is the hole, the stronger is the coupling between two resonators, and which results in this very nice anti-crossing regime corresponds to interaction between two modes. And the larger is the interaction, the larger is this energy splitting between two modes. The top is experiment data, and the bottom are theoretical data by obtained from theory. You can see that they look very similar, and the quality of the experimental results are quite high, despite this is a very simple setup. Actually, what is observed here is called Rabi oscillations, or Rabi splitting, or strong coupling. And if you go in time domain, so this is a frequency domain, in time domain that corresponds to oscillations with additional modulation. So it's not just, so you have oscillation at the frequency of the resonator and additional modulation provided by Rabi splitting, which is exactly this frequency of interaction. And that's Rabi splitting is well known in quantum mechanics, and it was first observed for spins in cavities. So it's spin electromagnetic wave interaction and what is called strong coupling regime, and reported first for spin systems or for pure quantum mechanical systems. So in a way, these two acoustic resonators allow you to immediately see like effects absolutely similar to quantum mechanical effects with a very strong Rabi splitting, which is compared to which is almost half. This Rabi frequency is equals to almost half of the eigen frequency of the resonator, which is okay. But just to be truly enough, this is not something fancy. This is a quite fast and dirty experiment, which was made by actually a high school student. So we use the sophisticated sound sources. Each of you have the same at your tabletop. This is a sophisticated data acquisition setup, just a MATLAB. And our specially designed 3D spatial frame based on boxes. And water level control system made out of bucket and some dirty water. And that's enough to do experiment, which, as I said, was done by last grade high school student. But now moving to, this was a closed resonator system. These are the plastic tubes you can buy in any shop, any construction shop. So now let's move to open resonators, to open cavities. And that is typical setup for acoustic scattering. Yeah, now we are not exciting the closed resonator, but we have a scatterer, then we we hit with the acoustic waves, and then you have some scattered wave, so incident wave, and some additionally rescattered wave, which encodes all the information about the scatterer and the physics beyond that. So, and at this moment, it's good to work not in the modes of, let's say, of a closed resonator like a Fabry-Perot, but you work in the basis of multipoles. Yeah, because you can expand. We know that any scattered field can be expanded into the series of multipoles. The first multipole in acoustics is monopole, just breathing type of mode. Dipole, it's just moving there and forth and back. And then quadrupole, which is like boom, boom, like this kind of an oscillation. And that set of modes allows you to control all the acoustics properties and predict and understand how does it work. Oops, I'm sorry. The interesting thing is that in acoustics, these two, the monopole and dipole, are the fundamental multiples. What does it mean? So it means that they give the main contribution to scattering for small particles. So here A is a radius of a scatterer, typical radius of a scatterer, and K is the wave vector. So this is basically size over lambda in cube. So these are much smaller, so this first non-zero contributions are monopole and dipole, and they are of the same amplitude. However, in optics, for example, you have only dipole mode. And that's why it makes quite interesting all the physics. And the control parameters, again, are the relative mass density and relative compressibility, which just control the properties of the scattering. Now, you can think of this oscillation. Yeah, these are just the illustration of how to think of these fields. Yeah. So the monopole is centrally symmetric, and dipole has a direction of symmetry. And for each of them, you can introduce amplitude of monopole and amplitude of dipole. And also, you can introduce polarizability, what we call polarizability. So it's coefficient, which is proportional, which gives you the connection between density and monopole response. So the amplitude of this mode is proportional to the pressure, and the coefficient is alpha m, I'm sorry. The same, your dipole, which shows the amplitude of this mode, of the field which propagates, is proportional to incident velocity. And this coefficient is what is called dipole polarizability. So we were able to introduce them rigorously in our paper, which is already 5 years from now in PRL, and they are connected. So it's very similar to what is done in optics, but we just made it for acoustics. I'll come back later to these expressions. Now, so what are the questions appearing here? So can we control scattering? Can we tune the parameters of material? And one of the big, not a problem, but fundamental things is that mostly for air acoustics, for airborne acoustics, the velocity of sound in air normally is much smaller than velocity of sound in any material, in most of the materials, whether it's wood, steel, plastic, or whatever. So for steel, this is one order, 20 times, velocity is 20 times larger, which means that effective refractive index of material, of steel, for example, is 20 times smaller than refractive index is just, relative refractive index is 1/20. So that means that for acoustics, for airborne acoustics, you don't have high refractive index materials. Basically, they are, because materials have high velocity of sound, which we know it. There was a question?
This ratio is inverse, right? It's greater than 1. Maybe it's less.
Oh, yeah, I'm sorry. Yeah, it's vice versa. I'm sorry, yeah. It's C over air, so it's vice versa. Thank you. And to overcome this problem, actually what you can use are metamaterials. So how people solve this problem? It's quite artificial way.